and I will talk about A64FX, SVE, and programming. This is my outline. First, I will briefly introduce Fugaku. Fugaku is the next generation supercomputer in Japan. RIKEN developed Fugaku along with Fujitsu. The public service of Fugaku started on March last year. Please show this URL for the detail of the information of Fugaku. Fugaku consists of 432 racks and totally over 150,000 nodes. The peak performance is double precision is lower than half exaflops in normal mode with 2 GHz, but using boost mode, it becomes more than half exaflops. Fugaku took first place in multiple supercomputing rankings announced at ISC 2020, such as Top 500, HPCG, HPLAI, and Green 500, and keep it 4 times in SC21. The processor of Fugaku is the Fujitsu A64FX. It is ARM-based processor and is the first processor to support SVE, Scalable Vector Extension. The A64FX is a many-core processor and consists of 48 compute cores. And internally, it is divided into 4 CMG core memory groups. A CMG consists of 12 compute core, an assistant core, a shared L2 cache, and memory controller. Assistant core is for dedicated processor for OS support. As for the main memory, 4 HBM2 stacks are installed in the CPU package. The capacity is 32 GB, and the throughput is 1 TB per second on chip totally. Detailed microarchitecture is opened in this GitHub, so please refer to this document. This slide shows the system configuration of Fugaku. A node consists of 1 CPU. All units include main memory network interface in a package. And 2 nodes are mounted on a board called CMU, CPU Memory Unit. A set of 8 CMU, that is 16 nodes, is called a bunch of blades, and 3 bulbs, that is 48 nodes, are installed on the shelf. 8 shelves are mounted in the rack. And consequently, 1 rack includes 384 nodes. Fugaku is a homogeneous system without accelerator, but there are 2 types of node in Fugaku. One is a compute node, and the other is a compute node with I/O node. But hereafter, we call just an I/O node, but I/O node is including that compute node and I/O operation. And compute node has 2 assistant core, while I/O node has 4 assistant core, because I/O node process I/O operation as well as computations. I/O node runs boost mode and cannot change user to keep I/O performance. In the I/O node, there are 3 types: BIO, SIO, GIO. BIO is a boot I/O node, and it is a boot server including boot storage. One BIO exists in 16 nodes or above. SIO is a storage I/O node, and it is a storage server including SSD of the first layer storage. One SIO exists in above. GIO is a global I/O node. It is a relay node over InfiniBand for FEFS, which is a cluster file system of the second layer storage. There are 2 GIO in a rack. So totally 50 I/O nodes exist in a rack. Next, I will move to details of SVE. As you know, current processor trends are many core and wide SIMD. For example, in many core, Intel Night Landing has over 16 cores, and AMD EPYC has 64 core, and A64FX has 48 core and 2 or 4 assistant cores. In the wide SIMD, Night Landing has 512 bits, while EPYC has 256. But there is a problem. No program compatibility between different SIMD lengths. So recompile is required between AVX2 and AVX512. In Arm instruction set, it has SIMD instruction named Neon from Arm v7 ISA, but it is 128-bit width. Arm cooperates with Fujitsu to improve SIMD instruction for HPC. That is SVE, Scalable Vector Extension. SVE is a complementary extension that does not replace Neon and was developed specifically for vectorization of HPC scientific workload. The new feature and the benefit of SVE comparing to Neon are as follows. First one is scalable vector length. It increases parallelism while allowing the implementation choice of vector length. VL can be chosen from 128-bit to 2048-bit by processor vendor. Second one is vector length agnostic programming, VLA in short. VLA supports a programming paradigm of write once, run anywhere, scalable vector code. Third one is a gather load and scatter store. It enables vectorization of complex data structure with nonlinear access patterns. Fourth one is per-lane prediction. It enables vectorization of complex nested control code containing side effect and avoidance of loop head and tails, particularly for vector length agnostic programming. Also, it is useful because vector length was widened, but some application is limited the vector length. For example, one structure has 3 elements X, Y, Z, and they are calculated independently. In that case, upper 5 elements is in vector register are masked, then it can be vectorized easily. Or 2 structures are stored in vector register, then upper 2 elements are masked and the 6 elements are vectorized. Fifth one is the predicate-based driven loop control and management. It reduces vectorization overhead relative to scalar code. It supports vector length agnostic programming for loop structure. Vector length agnostic programming is a specific feature in SVE. It enables same binaries to run on different vector length environment because of programming independent of vector length. SVE specification defines the vector length from 128-bit to 2048-bit by 128-bit. Each processor may support different vector lengths. SVE instructions don't have vector length information, but refer the value of LEN special register implicitly. LEN is a field of system register that specifies current vector length. If len is 1, then the vector length is 128-bit. If len is 4, then it is 512-bit, and so on. A64FX processor support 512-bit, 256-bit, and 128-bit, 3 types of vector lengths. This graph shows the registers for SVE. Z registers is as SVE vector registers. There are 32 vector registers. V register is a neon SIMD registers, which is overlapped with the SVE vector registers. The length of a V register is fixed to 128-bit, while the length of Z register is different in replacement, implementation, and setting. When LEN is 4, it supports 512-bit vector length. And it is possible to perform the operation to 64-bit by 8, or 32-bit by 16, or 16-bit by 32, 8-bit by 64 in parallel. The instruction is defined for LEN is 1 to 16, which is stored in the system register ZCR, and it is used to execute ISA implicitly. ZCR contains the vector length for each privilege level. P is a predicate register used as a mask flag to select active element for the operation. There are 16 predicate registers, but the normal instruction can specify only top of 8 predicate registers, and only other predicate register can be accessed for the special predicate instruction. The size of predicate register is 64-bit when LEN is 4. This is an example of simple SVE arithmetic instruction. FADD, FAD is a vector floating add instruction, and add all floating point element of the second source of vector register, here in the Z1 register, to corresponding the element of the first source vector Z0 register, and replace the result in the corresponding element of the destination vector register. Here is Z2 registers. So in this instruction, every element is added to each element. This instruction is unpredicate, so all elements are calculated. And this has 3 operands, Z1, Z0, and Z2 is independent, can be specified in the different registers. This example is for LEN is 4 for 512-bit case. In this presentation, I use this LEN is 4 is used. It can perform 8 operations for double precision floating point values, or 16 operation for single precision floating point operation, and 32 operation for half precision at a time. In assembly language, operand of double precision are specified of .d, and in the half precision case, single precision case, that is changed to the .s, and half precision case, it changes the .h. And another instruction, integer add instruction is exists for integer, and in that case, that is supports the several data type. For 64-bit is specified by .d, and 32-bit is .s, and 16-bit is .h, and 8-bit is .b. So these are the very simple SVE instructions. Next is the example with predicate instruction. This is also floating add vectors, but this is specified a predicate register. Here, the P0 is a predicate register. In this example, in predicate register is 10101010. So the even element are inactive, and odd element is active, only active. So according to this predicate flags, only active elements are calculated and stored to that result of the corresponding result. And predicate is specified by (m). This specifies that the inactive elements are unmodified. So in this case, inactive element is copied to that first operand is copied to that the destination. So, and in the assembler, the 3 operand can be specified, but it should be that the first operand and the destination operand must be same. So this instruction is destructive operation. This is the next example. This next instruction is the example of load instruction. Load instruction has several variations, and this is a continuous load with scalar plus scalar. It loads data to element of vector register from the memory address generated by adding a 64-bit scalar base and scalar index, which is multiplied by 8. Inactive element will not read device memory and set to 0. It's specified that the predicate /0 is specified that inactive element is 0 clear. This continuous load can access the data whose size is vector size is 1 memory access. This is an example of vector length agnostic programming. This is a simple DAXP program in just written in C. And left is that assembly program for Scalable code, and right is for SVE vector code. At a look, both one is almost same sequence. And this SVE code run with any vector length. In the Scala code, first set a constant 3.0 to register D2 and clear the loop counter X0. And X2 is a base address of array X, and X1 is a base address of array Y. They are initialized before this loop. At the beginning of loop, element of X of I and Y of I is loaded and calculated DuxP using FMA fuse multiply and add instruction. Then store the result to Y of I. Loop counter is updated and compare it with the end of loop. And if it is not the end, the loop is repeated. So very simple Scala code. And in SVE code, almost same sequence. First, set a constant to a vector registers. In this case, 3.0 is stored every element of vector Z0. In fmove, the immediate value is encoded to the 8-bit floating point with 1 sign bit, 3-bit exponent, and 4-bit fraction part. Then generate a initial loop predict using the file LO instruction. This file LO instruction is quite unique in SVE. So I will describe more detail by next slide. So here, understand that the predicate needed to execute the loop are set appropriately in the initialization. For example, loop counter is larger than vector length, vector element, the predicate is all active. And if the loop count is less than the vector element, the upper predicate element are inactive. So correctly. And the X10 is at the base address of X of array of X, and X11 is the base point, base address of Y arrays. And the beginning of the loop, the load two vectors and calculates them with the FMA instruction for vector registers. And store the result of vector register to the memory. These instructions using the predicate generated by the file LO instruction. So requested data is only operated correctly. And next, the update the loop counter using the incd instruction. This incd instruction increments the loop counter by the number of elements in a vector respectively. But this instruction itself has no vector length information. It refers the LEN field of system registers. Then generates the next loop predicate using the file LO instruction and check the end of loop by this conditional branch. If at least the first predicate is active, then the loop is continued. And if the all predicate is for inactive, then loop is terminated. This SVE code runs on any vector length. Also, this SVE code correctly runs for any n iterations by single loop. While any other SIMD code usually requires two loops. One is for multiple vector lengths and operated by SIMD, and another is the remains and operated by Scala. But using this predicate correctly, that is only single loop is enough to that all of repeat of that loops in any number of repetitions. And this is this instruction of file LO. File LO instruction generates predicate vectors. This is an example. This example, P1 is a destination predict, and X8 is a current loop counter, and X9 is at the maximum counter of loop. First, it generates each element counter. Here, a vector consists of 8 elements, so it generates loop counter from X8 to X8 plus 7 in temporal register. And each element in this vector is compared with the maximum loop values. This is the X9. Then, when loop continue case, every predicate is active and set to 1 in all elements. But when the loop is terminate case, the upper element, if that fifth element is at the end of that loop, then upper 4 case is inactive and 4 predicate is active. So this is correctly set up the predicate register using this file LO instruction. Next, I will introduce the FMA floating point multiply add instruction. In general, FMA requires 4 operands, 3 input and 1 output. Here, that in this case, that ZDN by ZM plus ZA to store to the ZDN. But instruction format is fixed to 32-bit and cannot specify 4 operands. So some input operand should be used for output. So FMA instructions are destructive. FMLA, FMAD is destroys the first operand. First multiplicand operand ZDN is same as that destination register and the first registers. So this multiplicand operand data is destroyed to that the result. And another instruction, FMLA, is also calculates that floating FMA floating point multiply and add, but this FMLA is destroys that the third addend operand is destroyed. So FMAD and FMLA is almost same instruction, but different is register destruction. And also, instead of that multiply and add, multiply and subtract exist. So FMLS and FMSB is that the difference of adding and subtraction. And also another instruction, negated fused multiply add is FNMAD and so on. So totally 8 types of FMA exist, but they are all of them is that the destructive instruction. But destructive assignment are generally processed for predicate arithmetic instruction, not just FMA, because ISA encoding to fixed 32-bit is very limited. Constructive operation may be achieved with instruction pair, prefix, move instruction, move prefix. This operation is the same as move instruction. The prefix move must immediately proceed the instruction and it can be merged. The same destination, predicate, and size and type case. Then the hardware can execute this operation as one consecutive operations. This implementation is hardware dependent and shows the implementation of A64FX is next slide. This slide shows that Fritz in A64FX, pair of move prefix and FMA3 instruction are merged to one FMA4 operation in pre-decode stage. To merge this instruction, the overhead of main pipeline is reduced. And several load store instructions are supported in SVE. They are basically divided for continuous load and gather load. Continuous load is a single memory access with vector length. So in L1, LEN is 4 case, the throughput of access is achieved 64 bytes per cycle. While gather load is multiple memory access with each vector element is target memory address. So in LEN is 4 and access double precision data, one gather load instruction generate 8 memory address and 8 memory access. And in generally, the throughput is the same as scalar access. That is 8 bytes per cycle in double case. But A64FX has some optimization mechanisms for gather load. I will describe it later. In continuous load, there are 2 types of addressing, scalar plus immediate and scalar plus scalar. I already described scalar plus scalar addressing. I will describe the scalar plus immediate in next slide. In gather load, there are 2 types of addressing, scalar plus vector and vector plus immediate. In scalar plus vector, the same array but different index are accessed. While in vector plus immediate, different array but the same offset are accessed. I will describe in detail later, but again, the gather load needs independent several memory access, so the throughput is lower than continuous load. This is the example of continuous load of double word with scalar plus immediate. It loads data to element of a vector register from memory address generated by the 64-bit scalar base with immediate index. The immediate value is in the range of -8 to 7, encoded to 4 bits, which is multiplied by the vector's in-memory size. If len is 4, 512-bit vector size, so VL is 64 bytes. Inactive element will not read device memory and are set to 0 in the destination vector. In this addressing, access data are aligned to vector lengths. The address calculation uses VL, but VL is referred to the value in the runtime environment. So vector length agnostic is realized. As shown in the figure, one memory access vector size data. Of course, this is implementation dependent, and here we show that such an implementation is possible. In fact, in A64FX, continuous load is implemented with one memory access. This is an example of gather load of double word with vector index. It loads data to active element of a vector register from memory address generated by 64-bit scalar base plus vector index. The index value are multiplied by 8. Inactive element will not read device memory and are set to 0 in destination vector register. In this example, the index are every 4 and are not continuous. So gather load are required. In contrast to continuous load, gather load have separate memory access for each element. In A64FX, gather load throughput is improved by combined gather. I will describe later. In A64FX, combined gather is implemented. When two data to even odd pair register, element 0 and element 1 are in the same in 128-bit byte aligned block, then the two memory access is merged to one memory access. So maximum bandwidth is improved to 32 bytes per cycle, while normal case is 16 bytes per cycle. In A64FX, another improvement for load performance is implemented. That is unaligned access. In normally, if the cache access is unaligned, the cache access is divided to access, and throughput is degraded. Intel processor is in this case. On the other hand, in A64FX, such unaligned load also achieve peak performance of cache access to 128 bytes per cycle. Even using combine gather, the peak throughput is 1/4 of continuous load. In double load case, it is important to be able to use continuous load rather than gather load to improve the performance, memory performance. And one of the good optimization is using the structure load. Structure load is loads that two double word structure to two vectors. For example, as shown in this figure, in memory, an array of complex number has alternatively real and imaginary parts. And LD2D instruction loads the array and store it in two vector registers. One holds only the real part, and the other one holds the imaginary part. The actual behavior is implementation dependent, but in A64FX, this structure load has the same peak throughput of continuous load. Therefore, the throughput is improved rather than using gather load to pick up only real part or imaginary part. This structure load supports up to 4 elements of structure. That is, LD2D, LD3D, and LD4D is only support. So not support to the over 5 displacement. So LD4D load data and store each element to 4 vector registers. There are also structure store to correspond to each structure load. In Fujitsu compiler, we use structure load and store for complex number if they improve the performance. SVE contains a large number of instructions. We do not have time to explain all the instructions. So if you're interested, please refer to the reference manual of SVE. That is a supplement of ARM architecture reference manual, and you can download from this URL by creating an account for free. And next, I will introduce how to log in to and use the Fugaku. To use Fugaku, first, you should access the Fugaku portal. I think you have received an email in advance telling you to this preparation and test until you can log in to the Fugaku login node. Are you completed? The access to the manual, how to install the client certificate, and how to start access to the Fugaku can be obtained from this URL, which is the same as URL, including the email to you. And if you have any question about cannot log into this portal site or login node, please ask to the technical support this email. But currently, that is out of support time. So if you questions, please tell me that please mail me. I will help you. And this Fugaku portal site has a lot of useful information for Fugaku. So please visit here. You should set up SH key to login node on this portal site. Also, several manuals such as user's guide, language manual, programming guide, etc. also can get this portal site. And report important information to Fugaku to also report it here, this portal site. And also get the operation status. Detail of operation status is get here, this portal site, such as how many jobs are executed, or how many nodes are available, or how many jobs are pending. And also these details are reported on this, this portal site. So I want to hands-on that each people, but not only all people get that the account of that Fugaku. So I will show that the hands-on result to the slide. But if you're interested, you will execute that this execution in yourself. And to access that Fugaku, SSH to login node is that the this host name login.fugaku.rccs.riken.jp. This login node name is that the automatically select one. Several login nodes exist, and automatically select one of login node. And once login, please invoke that ls command to check that your user ID and also that the group ID. In this case, that my login ID is L00227 and the group ID is RA020008. This this group ID is common to our this lecture student on this lecture. And we can share that the file in /share directory. /share RA02008 is can share with storage between our attendee of the lecture. So I put that the SVE sample directory to put my samples. So you can copy that my sample program and the sample script. And this is very simple program, stream.c. This is that very simple program for stream benchmark to evaluate that memory bandwidth. And compile.sh is the sample compile script for stream.c. And run1.sh is that the sample job script. And this how to compile that this program. I use that the FCC. FCC is that the Fujitsu compiler is and cross compiler for A6 for Fugaku. So FCC-PX is used at the login node. And also, if you access to that the interactive node, then you can use that the FCC to the Fujitsu compiler. And this -k first is that the optimize option usually used. So just using that -k first, then usually that the source is compiled optimized. And also OpenMP is that the option to that C flag, option flag for the OpenMP. And also opt message equal to and nless minus nlst equal t is the output compiler optimization message to special files. So this message is about how compiler is optimized that source code. So it is very useful to check that how compile is optimized. The source code is optimized. So please set this flag to check that the result. And I compile that the 3 binaries. One is that optimized to the SVE vector code. And I want to check that the SVE performance. So we try to generate that the binaries don't use that the SVE. That's specified by that -k no SVE. It's specified that the don't use that SVE instruction, but using that the SIMD code of Neon. So using that -k no SVE, that generates the Neon vectorized code. And if you want that no Neon and no SVE, then you specify that -k no SIMD. Then the compiler is generated that Scala code. Don't use that the SIMD code. So if you run this shell script, then it can generate the 3 types of binaries: stream.axf, stream.nosimd.axf, and stream.nosve axf. axf is that usually use that the extension of ARM binaries, ARM execution binary format. And also, it also generates that the list file. I show that the detail of this inside of this each compilation result. And in Fugaku, batch job scheduler is used. So you should create a job script to specify that job. So this is a sample of job script to run that 3 types of binaries. And in job script, several options should be set. This sharp PJM is that the specification for the job schedulers. And this PJM -L node equal 1 is specified that executes the 1 node. And the resource group is small is set to that the queue of that the job is entered. And in currently, Fugaku has several job queue. And one is the small, and another one is that large, and the third one is that interact. And the small jobs queue is the job for less than 384, less than 1 lakh number of nodes. And if you want to that less than 1 lakh, you can specify that the small job queue. And you want to specify that the another option that elapse. This elapse is the request time. So after this time is over, the job is automatically terminated. So it is necessary to specify a time with a margin. So if that the program is required the 10 minutes, then you specify that the 10 minutes. In this 0 colon 10 colon 10 is that the 10 minutes is specified. And since that the scheduler assigned for a free node by looking at this elapsed time, so it may be difficult to assign a job if it is a too large elapsed time. Then you should specify that this elapsed time is correctly. And also this PJM minus S is that specify that the creating a statistics file for jobs execution. And the statistics file is including the very useful information. So you had better to specify that minus S options. And you can invoke this job script using the pjsub command. So you may execute the pjsub this job script. Then job script scheduler is requested to the job and return to the job ID. In here, that is at very large number, but 12066932 is that this job numbers, job IDs. And the pjstat is that shows the result of jobs. So here, first invoke that the pjstat, then this job is will be start in that 9:49. Will means that will be start, and if that job is start, this parenthesis is removed, and you can look at the start time. And the job is completed, then pjstat has no result. So pjstat has no result, then the job is completed. Or you can specify to mail when the job is completed in that sum of option of that PJM. And if that job is completed, then standard out and standard error is put to that special some files. And also, if you specify that minus S, then the statistics file is also generated. So in default, that these files is specified by that this job ID dot error or dot out or dot stats. And in this result, we can compare to that the SVE performance, and using the SVE, that is about 94 gigabytes per second. But in this execution, that vector size, data size is only 1000. So this size is, this execution result is for the on the L1 cache performance. But in that L1 cache performance and sequential one core execution, one thread execution. But in this case, the SVE, using the SVE, that is about 94 gigabyte per second. While using the Neon, don't use that SVE, and using the Neon, that is 36 gigabyte per second. And using that Scala code, that is only the 23 gigabyte per second. So using the SVE, that is about 4 times faster performance. And using the Neon, that is at about 50% faster performance. And this performance is considered. The kernel loop of this program is this very simple loops. So 2 vectorize load and multiply and add and store to that another register, another vectors. So in each line required 2 load and 1 store and 1 FMA calculation. And A64FX can load 2 data or 1 store data. So in this loop, it takes about 2 cycles because that is dependent. The 2 load is 1 cycle and 1 store is 1 cycle. And FMA calculation is overlapped with that the load and store memory access, cache access. So it takes about 2 cycles in a loop. And in SVE case, each data is 64 bytes and run at 2 gigahertz in normal mode. So the peak performance is 128 gigabytes per second to the cache access. And the result is 94 gigabytes per second, so about 75% of the peak performance. And in Neon case, the same estimation is calculated, then that is about 32 gigabytes per second. But this peak performance is, but the result is 33 gigabytes per second. So rather than that, the peak performance estimation. This is because A64FX is has that right merge mechanisms. Right merge is that small multiple store is merged to that 32 byte. So using that the Neon case, each store is 16 bytes. So 16 store is continuous, 16 byte store is continued. So the A64FX is converted to that 16 byte store to 16 byte store to 1 32 byte store. So that is improved the performance to that the simple estimations. So the result is rather than some estimations. And also that the Scala case, it also. So the Scala case is peak performance is 16 gigabytes per second, but the result is 23 gigabytes per second. The reason is the same. And if you're interested, this is the case of the 1 thread and the on L1 cache data size. So changing the size of array and check that the performance of L2 and the memory access. And and I said that the compiler message can be checked using that the .list files. So we can check that this .list LST files. In the .lst file, the compiler message, compiler optimization message is included within that the listing of the source code and also that optimizing message. So in that, before that the loop listing, the several compiler messages exist. So looking this message, this program, this loop is generated that SIMD SVE code. It repeated, it represented by the SIMD VL8. So vector length is 8, 64 byte is used. So it this code is using that SVE is understand. And also this loop is software pipelining I described later. And if that the number of loop is over the 144, and 4 loop is software pipelined. And this loop is the including inside the specifies as the OpenMP pragma. So this loop is parallelized, so multi-threaded, using that this P is specified as multi-threaded. And also this 2V is specified that the 2 loop is unrolled, and that is vectorized. So you looking at this thing, it can vectorize using that SVE. So if you compile that your program and not good performance, then you can check that this LST file and check that the kernel loop is vectorized or not. And also these messages listed as optimizing messages. Also, this message is said that the SIMD, this line is SIMD conversion is applied. And also this loop is software pipeline. And also this software pipeline is greater than or equal to 144. So if you look at this list of files, then you can understand that how the compiler is optimized this loop. And I explained that the software pipelining. So software pipelining improves the instruction level parallelism in a kernel loop by overlapping the current and the next iteration of loop with in-order execution. In this description, assume that the machine model is different of the A64FX in simplicity, and the load latency is 3, and number of function unit is 3, and the number of commit is 4. This is the assumption of this model. And it considers that this simple C program, that is vector add program. And this program is compiled, and the C don't use that the software pipelining. Then that is that the to load and add and store. So simply this 4 instruction is calculated this one loop. But each instruction has latencies. So currently load latency is 3. So this add instruction is cannot execute that just after the load, but require the latency. So 3 cycles later, this add instruction can be executed to using that the load data. And also this store can be executed after the 3 cycles executes this add instruction. So each instruction has latency. So the execution of this loop is it takes about 7 cycles to one loops. So, but using the software pipeline, each instruction of each loop is arranged to one simultaneously. So, two load is for one loops, and this add instruction is another loops, and this store is the another loops. So this color is specified as the number of loops. So the first load, so this pink load is the data is uses the next iteration of add, and the this store is the after loops is stored, but the different loops of execution, but the total of 2 load and 1 add and 1 store can be executed in a cycle. So using this software pipelining, the loop is very fastly executed to execute the function action in a cycle. So the pipeline is the loop is very efficiently executed in using the software pipelining. And usually this software pipelining is a special technique for that in-order execution processors. And current processor is support the out-of-order execution in hardware. So if that the infinite resources of hardware exist in the out-of-order resources, then this software pipelining manner is automatically in hardware. But in realistic, that the resource is limited, and the resource is limited. So only that the hardware out-of-order execution is not perfectly matched the each instructions. So, and especially in A64FX is that the throughput-oriented instruction, and something the small resources of for out-of-order resources. So this software pipelining is improved the performance in A64FX. And this is that the sample code of this stream.c. So and this stream.c, I specify that the restrict attribute in each array of the operand in that kernel functions. And if this restrict is not exist, how is that the performance is different. So I tested deleting that the restrict attribute, and compiled that another binaries. So stream 0.axf. In that case, looking at the list of file, then the list is specified at the 2s. Previously, that loop is 2v, to unrolled and vectorized. But in this case, that is unrolled two loop is unrolled, but that is using the Scala code. And also the optimizing message is also says that the SIMD conversion is not applied to this loop because the uncertain order of the definition and the reference of variable y may be different result from serial execution. This means that the vector of x, this vector of y may be overlapped with x1 or x2. So in that case, that is vectorized, then this y1 is, if overlapped, then that is collapsed, that's the result. So the compiler is not that vectorized. But usually another compiler is not support assumption that this argument array is not overlapped. So another compiler such as GNU compiler or ARM compiler can generate the vector code without the restrict attribute. But Fujitsu compiler is some restrict in that is strict about the overlap of registers. So Fujitsu compiler, using the Fujitsu compiler, you must specify that this restrict attribute to the operand of vectors. Or you can specify that don't overlap, the array are not overlapped is specified that the compiler option. That is rest p equal arm is that the specification, that the compiler options. Then it can also generate the vector using the SVE without that the restrict attribute. So I check that this result. So this compiler compiling that using the so I think that the rest p equal arm is added the compile, then that is correctly or can optimizing that using that vectorized in the same source code, but that is this option is can apply to the SVE vectorization code. And also that is the result is also that very different, that if that the vector is not applied that the vector code, that is only 10 GB per second. I don't know why that is the less than the Scala code, but that is the result of my result. And if that specify that the rest p, then that is about 96 GB per second, almost same as that adding that the rest p attribute. So if you take care that if your program is not the good performance, then you check that the kernel loop is vectorized or not. And if not vectorized, then if you specify that the compiler message is such as this uncertain order, such kind of message, then you try to use that adding the rest p restrict attribute or adding that compiler option of rest p. And I said that the GNU compiler and ARM compiler is don't use that this rest p option. And also Fujitsu compiler has two modes. One is the Tourade mode, and another one is the Clang mode. And Clang mode is using that the front end is a Clang LLVM open source compilers. So using this Clang mode, that compiler is assumed that each array is not overlapped. So using that and using that the Clang mode, you specify that the -n Clang. Then you can use that Clang mode. Then you check that the list file. Then this is different in that the Tourade mode case, but that is specified at the V. So this loop is vectorized. But I checked that the performance, but this Clang mode result is only 60 gigabytes per second. I don't know that why that this Clang mode is not good performance. So I checked that the assembly code using that -s large S option. It generates that the not binary but the assembly code, and look at this kernel loops, portion of this kernel loops. Then that is that using that this code. This is that the kernel loop execution. So look at this. 3 load instructions exist. One is L1D, and 2 L1D is the same as Tourade mode case. And this L1RD is that specifically adding this Clang mode. And the L1RD is that the broadcast to that register is one memory element to broadcast that the vector register. So this instruction is for that this C0 data. So I don't know that reason, but using this Clang mode, this C0 is loaded to the every loops. So that is requires the 3 load and 1 store. So it takes about 3 cycles, and it reduces the performance. And also the other instruction is also total instruction is also many instructions. So maybe it's specified that some optimizing option to specify the Clang mode, then it might be the improved. But I did not know that fixed one. And I also looked at the Tourade mode result of assembly code compared to that the previous Clang mode. So that is the result of the Tourade mode kernel code. So that is that totally that 7 instructions, and 2 load and 1 store and 1 FMA, 1 computation instructions. And this is almost the same as the example of vector length agnostic case, but it using that this code does not use that the file LO. So that using that the vector length agnostic programming, and using that the trapped mode Fujitsu compiler using that the fixed vector length optimization. So in this case, this is that optimized for the fixed to that 512-bit vector length. So don't use that the vector length agnostics. So if you want to get that vector length agnostic code, then you must specify that the option to use the vector length agnostic specification to that compiler. And also, I'm sorry, this code is that using that the no software pipeline case, because using the software pipeline, that assembly code is very, very large in a loop, because that the many loops is combined to that one loops. So I using that this, so I usually look at the assembly code in simple code. I specify that the no software pipeline and no unroll is specified to how to compile that the source code. So in this is that the some don't use that the software pipeline optimization, but this is very simple code. So in this case, don't use that the software pipelining. It can achieve that the about 80 gigabytes per second, and don't use that the software pipelining, but using that unrolling automatic compiler automatic unrolling, then that is improved the 83 gigabytes per second. So because of this loop is very simple, so don't use the software pipelining. The performance is good, but usually software pipelining is effective in the A64FX. But also software pipelining is sometimes reduce the performance, because that if that the loop body is too big, in that case that the register spill is happen, so the performance decreased. So in the A64FX case, the software pipeline is that good and good point and bad point. So you can select that the using that software pipeline or not. So that depends on that your program. And also this stream program is compiled with OpenMP program. So I changed the number of threads to compare to that the SVE and no SVE. So in that one CMG, so change it to the 1 thread to 12 thread. In this case, the 1 thread case, that SVE is very good performance, but it depends. And also, this run is that large data size to so access to that memory. In that case, the 1 thread execution is good. Using the SVE, that is good performance, but that is about using that 4 thread. That is the performance is saturated, because almost that the peak of that memory performance that is that is limited to that memory performance. So in A64FX, 4 thread is using the SVE. 4 thread is saturated that memory performance, but only use that neon case that is not saturated the 4 thread, but 8 threads that is saturated the memory bandwidth. Also, no similarly, Scala code case, it also saturated the performance in 8 threads. So over the 8 threads, the performance is almost the same in the using the SVE and not using the SVE. But in other words, 4 thread is enough to that using the SVE, but 8 thread is required to the don't use SVE to using that the memory bandwidth. So so that is the result of the multi-thread execution in that the memory band is a limited applications. And this is up to 12 threads. So this is executed the 1 CMG. That is the NUMA domain. But A65FX can support the multi-thread to up to 48 threads in the processor, so between that CMG. But that is something requires some settings. If there's no setting in the or is that the default setting, the performance is not scalable to 48 threads. That or the slightly decreases the performance. This is because that in default, memory is allocated at the program load time. At that the using the CMG, only use the CMG. So the core on the other CMG access to the memory via the CMG. So the performance is not scalable to the total of the processor. So you can specify, or you can define that the environment variable of that the paging policy to that demand. This setting is changing the paging policy to demand. And in another word, it's the fast touch policy. In that case, that using that the several CMG, then and correctly touch that fast touch is correctly execute, then the memory is allocated to that each CMG to locally allocated the memory. So in that case, using settings of this environment variable, then that is increase the scalable increase to the up to 48 threads. But that performance improvement is in proportion to that number of threads. This is because that the thread affinity. The in default thread affinity is close in A65FX. In that close, that each thread is assigned to from in order from each CMG 0. So in this graph shows that the each CMG has 4 cores and totally 4 CMG, and assigned to that 6 threads. So first 4 thread is assigned to the CMG 0, and remains 2 thread is assigned to CMG 2. So in that case, only 2 CMG or 2 CMG's memory bandwidth is used to that in this case. So that not good performance to get using this default settings. But in the A65FX can specify that the several thread affinity. One is scatter affinity, and another one is a compact. Using that scatter affinity, it interleaves the thread to each CMG. So in this case, first thread is assigned to CMG 0, but second thread is assigned to CMG 1, and third one is CMG 3, and fourth one is CMG 0, 1, 2, 3. So interleave to the thread. Using this scatter affinity, then the total throughput is up to 600 gigabytes per second. Only use the 12 thread, because that in the closed case, 12 thread is only that 1 CMG, but scatter case, 12 thread is using the 4 CMGs, so 4 memory stacks. So it achieves that good memory performance in small thread. And another affinity is compact. And compact is also that using that evenly use the CMG, but continuously assigned to the thread. So in this case, 1 and 2 thread is assigned to the CMG 0, and 3 and 4 is assigned to CMG 2, CMG 1, and CMG thread 5 and thread 6 is assigned to CMG 2 and CMG 3. But in this slim case, that scatter and compact is almost same performance. But if that the L2 cache is shared to the L1, thread 1 and thread 2, the compact is maybe that better use of L2, use of L2. So compact is maybe that good performance in using that L2, commonly used that L2. And also, if all that 48 thread use, then this close and the compact is the same thread affinities. So, so using that 48 threads, the peak performance is almost same that each thread affinity. But the number of threads is small, then large differences exist in this stream benchmarks. It depends on that application, but the memory bandwidth limited program is usually that such behaviors. And this is that the how to specify that the scatter and compact. In the scatter case, that is only that one setting to every number of threads. But to the compact case, it depends on that the number of threads. The environment variable setting is depend on that the number of threads. So this is that example of the 32 thread case. And also this is a script. It can automatically calculate the settings to each any number of threads. And this is the last example. And the peak performance of this thread stream is 600 gigabytes per second. But we announced that the peak performance is about 800 gigabytes per second in A64FX in stream benchmark. This is because that this 600 gigabytes per second is that the application bandwidth. And in the hardware point of view, the cache, to keep that the cache coherence, a portion of cache is written, the previously load that data, memory data to cache. So in that hardware view, the stream benchmark is required the 3 read 1 store. So application level 600 gigabytes per second is required to that about 800 gigabytes per second in that memory bandwidth. But the stream benchmark case, the all cache data is write to that program. So there is no need to the preload is required. So such kind of optimization is available in the Fujitsu compiler with Z-fill optimization. Z-fill is using that the some instruction. That instruction is allocate L2 cache and clear that L2 cache. Using this instruction, that is not don't use that the preload to that memory. So the peak performance is the same as the application level memory bandwidth is the same as that memory bandwidth. So using this Z-field optimization, it can achieve that the 800 gigabyte per second in application level memory bandwidth. So using that the Z-field optimization, this Z-field and also specify that the software prefetch should be specified. But these Z-field and software prefetch can be set that the appropriate distance of load. But if you don't specify that the distance, then the compiler is automatically set that the some good distance. So you can only set that the Z-field and prefetch sequential option, then you can get that the good performance in the memory bandwidth using the Z-field optimization. So that is the finish of my lecture. So is there any question? ちょっといっぱい来てるのか。So I'm sorry, I didn't look at the chat. The login node is that the Intel processors. So login node and compute node is different processors. And もう答えてもらってるか。And oh, I'm sorry. So currently that maybe that the Fugaku is something crowded. Then you can use that the interact node is some high priority. So Sato-san is said.